Okay, here we'll take a few minutes to look at number 5 from the 2012 AP Calc AB exam. This is also on the BC exam, so this was another problem that appeared on both exams. But the problem setup is written here, and then they give you this differential equation. And this is going to represent the rate of change of the weight of a bird over time. And B would be the weight of the bird in grams. They tell you up here that when t is equal to 0, the initial weight of the bird is 20 grams. And then they go on to say that the solution to this is going to be a formula that would model the actual weight of the bird at any time t. So in part A, it wants us to figure out if the bird is gaining weight faster when it weighs 40 grams or when it weighs 70 grams. So if we can determine what the rate of change of the weight of the bird is at these two weights, we're going to be able to answer that question pretty easily. And this is actually very simple to do. You do have to kind of be careful with your evaluation here, because these are values of the dependent variable b. This rate actually depends on the dependent variable b, which is kind of weird. We're not used to seeing that. We're used to seeing these rates depend on the independent variable t or x. So if we want to know what the rate of change of the weight of the bird is at a weight of 40 grams, we're just going to take this b value, put it in place of b, and evaluate. And when you evaluate that, you get 12 grams, and then 12 grams per day, excuse me. The units of this would be grams per day, because the units here are grams, the units of b are grams, and the units of t are days. So the units of this rate are going to be grams over days, or grams per day. And then at 70, if you evaluate this rate of change there, you end up with 6 grams per day for the rate of change of the weight of the bird. And that tells us that the bird is obviously growing faster or gaining weight faster when it weighs 40 grams as opposed to when it weighs 70 grams. In part B, they want us to actually find the second derivative of this with respect to t. And so what we're going to have to do is we're going to have to do the derivative on the left side of the equal sign. We're going to have to do the derivative of what we have on the right side of the equal sign. Now before I did my next derivative, I wanted to distribute, just to simplify this a little bit. And I end up with this. And if you're not very, very careful when you're taking the derivative of this with respect to t, it's very simple to miss. The derivative of this with respect to any variable is going to be 0. But the derivative of this with respect to t is not just negative 1/5. B changes over time. B is the function that represents the weight of the bird. So this is a function of t. So whenever we take our derivative with respect to t on each side, we do get the second derivative on the left, like we mentioned a few seconds ago. And then on the right, the derivative of 20 is 0, so it's gone. The derivative of this is going to be negative 1/5 b to the 0. But then we have to use implicit differentiation here and multiply by the derivative of b with respect to t, since it definitely is a function of time. And so our second derivative can be simplified to look like this. We can just put what we know db dt to equal, which is right here. We can just put that in place of db dt, and so we get negative 1/5 times the original derivative that we were given. Now what they want us to do with this derivative is see if we can use it to help us figure out why this graph cannot represent the solution to the differential equation. Now if you look at this second derivative is, well, this portion is always obviously going to be negative no matter what b is, no matter what t is. This is the portion that is going to change at some point. Once you get to the b value of 100, this quantity right here is going to become negative once b exceeds 100. So as long as b is smaller than 100, it should be pretty obvious that this set of parentheses, 100 minus b, this quantity, is going to be positive. And if you have a negative times something that's going to be positive, as long as b is less than 100, and for the portion of the graph that we're looking at, b is less than 100, your second derivative is always going to be negative. The reason why this can't represent that, check out this portion of the graph. This is definitely concave up right here, and our second derivative would have to be positive in order for a graph to be concave up, because this second derivative cannot be positive when b is less than 100, we know that this can't be the solution graph. In part C, we're actually asked to find the solution. So it's just a separable differential equation, so we'll multiply each side of this differential equation by dt, divide each side by this set of parentheses. Now you do have to use a u substitution to take the integral on the left-hand side. That's what you're going to do after you separate your variables to get the solution. And if you're careful, you realize you pick up this coefficient of -1, or this constant of -1 that wasn't initially there, so we've replaced the original denominator with u, we've replaced db with what we've determined db to be equal to, and then the antiderivative of this is natural log of the absolute value of u. Make sure you recognize you still have that negative there, do your back substitution, put the original expression back in place of u, and then the integral on the right hand side, so coming from here clear down to this line, pretty simple, just 1/5 t, and then you have to put your constant of integration onto that side, so plus the c. And then we want to solve this for b. So when you exponentiate on each side to get rid of your natural log, you end up with this expression here on the right. Now you're adding within this exponent, and we add within an exponent when we multiply like bases. If you rewrite this as multiplication of like bases, e to this power times e to this power, the c power, you end up with something here that is going to be some numerical value. We don't know the value of it because we don't know the value of c, but e to a power is going to be some number. If we re-represent e to the c with a, what we do is we allow the right side of the equal sign, which is a product of two exponentials right here, to go from an expression that can only be positive. E to a power is only going to be positive, e to a power is only going to be positive. So this expression is only allowed to be positive, and that's why I still have the absolute values over here. But the instant I re-represent e to the c with a, I've given the right hand of the equation a way to become negative. And since I've given the right hand of the equation a way to become negative, I can drop the absolute values on the left. The left-hand side of the equation can now also be negative. And then if what I did was I actually thought about adding my b to this side and then subtracting ae to the -1/5 t from the other side, and I end up with this. So once we have our general solution here, we just have to apply the initial condition, which tells us when t is equal to 0, b, the weight of the bird, is equal to 20. So we put 20 in place of the b, we put 0 in place of the t. E to the 0 is 1, so this is just 100 minus a. Well, if 100 minus a is equal to 20, then a would obviously have to be 80. So when you solve this for a, you get 80. And then our specific solution, or our particular solution, is going to be this right here.